Welcome back to episode 3 of Finance Mathematics Demystified. This is the second installment of the volatility section. Just to remind you, we've looked at expected returns, we've looked partially at volatility, particularly concerning standard deviation, and we're going to be finishing volatility today, the relationship of volatility to risk and actually calculating standard deviation. And that will pave the way for us to go into a lesson on covariance, which will lead to diversification of portfolios, which will eventually lead into efficient frontier and many other risk management and portfolio management ideas. But you'll hopefully remember that we ended the last lesson looking at the relationship that standard deviation has to the graphics produced by these random walks, which were meant to mimic different kinds of stock returns, right? So we went through that, and we'll be beginning today's section, continuing volatility with actual calculations of standard deviation, and then moving on to describing the link between standard deviation, volatility, and risk. So, moving on to an actual calculation of standard deviation. A definition of standard deviation from just Google is a quantity expressing by how much the members of a group, so a group here is a set of numbers, right? And the members are the individual numbers. How much do the readings of a set of numbers differ from the average or the mean of that set of numbers, right? In other words, if I have a stock that's continually increasing by a couple of percent each year, right? If I look at the actual percent increases each year, how much do those differ from the average increase it has each year? This is that dispersion, that spread from the expected value that defines volatility, okay? This is the formula here. If you are a maths person, that's what it looks like. Here are the definitions of the terms. This little loop with a hat on top, sigma, that's standard deviation, and it's expressed as the root of some sum of values in our data set, our returns, and the difference that they have, the subtraction, from the average value, and then we square that and we divide by the number of data points that we've got, right? That's the standard deviation. That's how we get this, right? So, using a very simple example, if we have a data set of 5 numbers, 2, 4, 4, and 5, and yeah, this isn't percentage returns, it's just a demonstration. You get your mean, add them all together, divide by how many there are, get our mean of 3.8. Then what we do is we subtract that from each number in the data set, minus 1.8, 3 lots of 0.2, and 1.2, okay? We square those here, we add all of those up, that's this bit here, the sum of the differences squared. We add all of these up, get 4.8, divide by the number 0.96, take the square root, 0.98, that's our standard deviation of this data set. So that's that. You won't often have to do this by hand. If you're actually doing this as part of a job or you're doing it for your own use case, use a calculator, use an Excel spreadsheet, right? Especially if you're looking at hundreds of returns over the course of a year for an asset, right? Or multiple assets. You'd never do this by hand. So earlier I talked about these random walks and the values that fell within these shaded red region, and I said, oh yeah, roughly 68% of the simulations of the possible movements of this price fell within that standard deviation band. What did I mean by that? Why is that important? Well, there's this thing called the 68, 95, and 99.7 rule, which basically says if you have some set of numbers and the values in those sets are normally distributed, they follow a bell curve, right? When you work out the standard deviation of this set of numbers, you would expect that 68% of the values fall within one standard deviation either side of the mean, right? That 95 would fall within 2 standard deviations of the mean, 99.7 would fall within 3 standard deviations of the mean. And below, I've got a demonstration of this, right? In this image, I have a histogram or a bar chart of the daily returns of the S&P 500 over, I think, 5 years or maybe more, right? That's this histogram here. Daily percent returns marked on the bottom, right? I've overlaid onto this a bell curve or a normal distribution that's mapped to the same data, That's this smooth curve here. And then based on that bell curve, I've drawn in the one standard deviation either side of the mean line vertically as this red dotted line. So that means if I was to look at all of the daily fluctuations in the value of the S&P 500, I would expect 68% of those values, of those daily returns, to fall within the mean, which is going to be some slightly positive number, slightly more than 0, but you can't really see it on the graph here. So that's what we kind of understand. The importance of this is when I'm looking at an index or an asset, I know the likelihood that that value on any given day is going to increase or decrease by a certain percentage. This is useful when we start to think about things like risk or crashes, because we can say, oh, today this stock has decreased by 5%, and 5% is really big. There's only a 0.5% chance that this would have happened, right? You know, this is more than a 2 standard deviation or a 3 standard deviation shift in price movement. That signals to you this is a very extreme market activity that's going on right now. So when you're looking at this, you might realize the bell curve doesn't really fit the actual histogram very nicely. It doesn't fit the bar chart that well, for a couple of reasons. The actual histogram, it's much taller at this mean, right? There's a lot more values that are tightly packed around the mean. And then as we get to the edges here, there's more outliers of extreme decreases or extreme increases that occur on a daily basis. So this is normal, right? The bell curve, the normal distribution, is an approximation that we make of stock movements that makes a lot of mathematics a lot easier, but it's not 100% true. It's often good enough to make good forecasts, but stocks don't quite move this way. This observation of extreme events occurring more often than a normal distribution predicts is called fat tails. Real stock movements, returns, have what's called fat tails, and it means that extreme events are more likely than our models predict, right? This is important when we look into extreme value analysis, which, as I mentioned earlier with understanding standard deviation, helps us understand when we're in really unlikely scenarios, when there is a market crash, when a particular asset or a stock is crashing, right? How much is it likely to crash by? How much of our value is at risk when we're investing in an asset and a negative market event occurs? It's really important to understand the real distribution of our returns in these fat tails when looking at that kind of analysis. You'll also notice that it's slightly asymmetric. This portion of the tail here is higher up, thicker than this thinner extremity out here, right? But there's a sort of more bulk of positive returns in these low to moderate return region, and this sharp drop off here, right? So this should intuitively match our understanding of the market, that generally the market increases slowly and steadily, compounding day on day on day, but occasionally there are market crashes and big dips in market value. So those big dips and crashes are these extreme decreases in daily percent returns of the market, but that slow continual growth is this bulk of small to moderate returns on the positive daily return side. So standard deviation and risk. Now that we kind of know what standard deviation is and what it means in the context of price movements, how does this relate to risk? So I said at the beginning, there's a common misinterpretation that volatility and risk are the same thing. They're not. So volatility can indicate risk, but they aren't the same. Standard deviation, as we've seen, is a statistical measure of volatility, or the spread of price movements, right? That helps us gauge the relative riskiness of different assets. The reason why this happens is because if we look at the S&P 500 and we plot its actual daily returns on a graph like this with time, and I draw in that plus or minus 1 standard deviation band in blue here, you'll see the majority of values fall within this band, okay? But here are the extreme events that we talked about, the tail activity, okay? So volatility normally, or the standard deviation, I should say, if you're assuming normal distributions, it's not biased. It doesn't assume that there are more negative daily returns that are extreme than extreme positive daily returns, right? So the standard deviation kind of tells you how often you would expect extreme negative events to occur and extreme positive events to occur. And when we look at this, right, you can see we have these highly volatile regions here just after 2020. This is COVID-19. This is what the market did at the onset of COVID. Okay. And then here's the bear market of 2022. Some extreme behavior, some extreme gains, but ultimately more extreme losses in this bear market, right? A lot of activity outside of the standard deviation, right? The expected market behavior. That's what made it a bear market. Well, no, it was a bear market because it was decreasing in value and market sentiment was negative. But, you know, we also saw market behavior that was outside of the expected range of behaviors, okay? And this was a crash, which was a very, as you can see, extremely outside of the expected range. Risk, normally, we think of it as the likelihood of a negative event happening, the likelihood that there's going to be a crash, the likelihood that I'm going to lose money today, right? So as the standard deviation or the volatility measures both the positive and the negative extreme changes, or just changes and fluctuations in general, risk is usually only the changes that indicate the possibility of a negative event occurring. So, you know, you might just look at the extreme negative changes and then you would be approaching an idea like the Sortino ratio of describing volatility, or describing risk actually, right? But normally in finance modeling, we just look at all volatility as a measure of risk. If a stock gets really inflated and has high gains, then maybe it's about to crash. And if a stock is having very strong negative movements, it might continue to have strong negative movements. Either way, the point is, when there's a lot of movement, it's difficult to predict where that movement is going. That's inherently risky. So the ideas are linked, but they're not the same. So finally then, moving on to variance. It's very, very closely linked to standard deviation. This section is very short. Variance is just the square of standard deviation. You just take your calculation for standard deviation, you square the number. That's variance, right? The standard deviation is very intuitive because I told you within 1 or 2 or 3 standard deviations, you can kind of intuit like, oh yeah, this percentage of outcomes is going to be within this range, right? And you can reason about it in this intuitive way once you understand it. Variance doesn't really have that same interpretability as the standard deviation. Variance is really used more for the mathematical calculations. It's got some properties that make it perform a lot nicer. So the example from the earlier data set, we got a standard deviation of 0.98. The variance means we're going to square that, get 0.96, right? That's our variance. So it's not expressed in the same units as the original data. That's part of what makes it less interpretable and less intuitive to think about variance. This is why volatility is usually expressed on paper using the value of the standard deviation. But mathematics usually uses variance in calculations. The reason why is also partially to do with the fact that there's a very close brother of variance called covariance. They're heavily related, and you can tell by the name, it's covariance. And it's important for trying to understand the volatility of the movements of a collection of assets, many assets in tandem, in unison. If I've got a portfolio with 20 different stocks in it, right? I can't just look at the volatility of each individual stock and understand the volatility of the portfolio. No, I've got to understand the volatility of each individual stock and how those stocks move in relation to each other over time. And that's where the covariance comes into play. That's where it's used in mathematics. And that's why we use variance and covariance more often in calculation. The next lesson is going to be on covariance, so you'll begin to see what I mean with this. The last important thing that we have to cover for this lesson is annualizing volatility, right? So if you've got your daily data from whatever data source that you've got, and you understand the volatility of your market, of your index, of your fund, of your particular set of stocks, right? How do you go from a daily volatility to an annual volatility or a monthly volatility, and then do monthly or annual forecasts, right? How does that work? Well, you take a daily volatility, and there's 2 ways to do this. If you're working with variance and your time period or your variance is daily and you want to work out your annual volatility, you times by the number of days that are in the time period you're trying to approximate or get the volatility for. So I have daily volatility. I want annual volatility. So I times the daily volatility by 252. That's because that's the number of trading days in a year, okay? To annualize the volatility using standard deviation, it's very similar, but instead of multiplying by 252, you multiply by the square root of 252, and that gives you the same answer. So like I said, just make a mental note. There's 252 trading days normally in a year, not 365. If you don't take that into consideration and you do your forecasts, you'll end up with very optimistic projections that won't match reality, right? So you've got to be aware of this. And then that concludes this whole lesson on volatility and standard deviation and variance. So we should now understand standard deviation, how it's linked to volatility, why it's important, its relationship to risk and therefore risk management, right? And I've hinted at the future lessons. I've said that we're going to look at covariance next to understand the volatility of entire portfolios, and that's true. But these concepts also lead to the Sharpe ratio, which is a measure of risk-adjusted returns, right? I see some return in my investment over time, but what's the projected risk adjusted return, okay? What's the return per unit of risk I took to achieve that return? And then that plays into concepts like efficient frontier, which is a tool or a framework that we use to optimize our portfolios. So I hope that's been valuable for you. If you're interested in sticking with this session and this series and seeing the efficient frontier, seeing how to manage risk in your portfolios, understanding these concepts, stay around. The next part is going to be on covariance. See you there. Bye.